Good morning, everybody. Please find your seats so that we can get started with the third session. Thank you. The first talk in the third session will be presented by Hannah Emnet, and it's about a novel whisker sensor to detect 3D contact points and to extract contours.
Hello, everyone. My name is Hannah Emnet, and today I want to talk to you about developing the sense of touch for robotics. Our bio-inspired approach involves using artificial rat whiskers. Rats have amazing tactile abilities and can use their whiskers as their primary way to navigate, even in the complete darkness. What's even more amazing about rat whiskers is that there are no sensors along the entire length of the whisker, and instead, all sensing happens at the base of the follicle. The relative simplicity of this system makes it especially alluring for robotics. They can be used in complement with the visual system, should a camera fail, or in places where cameras cannot be used, such as in partially occluded spaces, muddy water, or sifting through sand. Some recent examples in the robotics community show the increasing interest in rat whisker sensors. However, few of these works have actually created a truly biomimetic rat whisker and follicle system. How is it that a rat whisker, which is essentially a stiff hair, can predict a 3D contact point location? Well, we know when a rat whisker impacts an object, moments and forces occur at the base of the whisker. These can be measured with an appropriate sensor. But how do you determine the 3D object location? Using the transverse moments, my and mz, you can estimate the angular deflection. But the radial distance along the length of the whisker is much harder to obtain. In previous studies, such as those I showed earlier, the time rate of change of bending moment magnitude was used to determine the radial distance. But this requires temporal information. A recent study in soft robotics suggests that there's a unique mapping between the magnitude and the direction of the bending moment and the axial force with the 3D contact point location. This means that in theory, a rat can determine where an object is impacting its whisker at each instant in time. This method of determining radial distance and the novelty of the present work is that you do not need to rely on temporal information and can instead create a direct mapping between mechanics in the 3D contact point location. So the soft robotics study did this in simulation. We set out to show proof of concept in hardware. We developed our sensor based on a Maltese cross configuration, and we specifically chose our whisker to be linearly tapered because the linear taper is essential to creating a unique mapping. Our sensor had 8 strain gauges top and bottom of the cross, which completed 4 half-wheat stone bridges. During a deflection, the arms of the cross bent in tension and compression. The change in resistance caused in the strain gauges gives you a value that's related to the transverse moments and the axial force. Our fully assembled follicle is shown on the bottom here, and we chose our follicle to be about 5 times the scale of a real rat whisker. We next collected data at almost 200 static contact points. We then simulated the data, the mechanics at the base of the whisker, using a quasi-static whisker bending software. The idea here is that if we can force our sensor's outputs to match simulation, then we can treat simulation as ground truth. We then can compare our simulated results to our calibrated experimental data. And you can see we get fairly good matching, with clear degradation at the larger magnitude signals, which correspond to large angular deflections. But we wondered if we even needed to combine our signals to match these mechanical signals, like moments and forces, or if the specific geometry of our system, specifically the linear taper, was enough to permit a unique mapping. So we then compared our predicted we actually mapped from the sensor's output directly to the 3D contact point. And we can compare our results here. And you can see that these results suggest the potential for high-quality contour extraction without any calibration at all. We can then test the performance of our sensor, and you can see here on the top left, I'm showing you a real rat whisker impacting a peg, and our 5x scaled rat whisker also impacting a peg, with the voltage traces shown on the bottom. After a collision, we can convert these voltage traces directly to a 3D contact point location. Extending this idea, we can then perform contour extraction. So we did that for a cone and a cylinder. And in this next slide, I'm going to show you the known positions of the cone and the cylinder and the 3D points that the algorithm actually predicts. And you can see that these 3D contact points either lie directly on the cylinder or are very close. A further extension of this idea would be actually put this on a robot arm and do real-time behavior modification. So what I'm showing you here is that as this robot impacts different objects, it starts tapping faster, just as a real rat would, like earlier in the presentation. Another further application of this would be to create real-time point clouds of your environment, perform object avoidance, and we anticipate it could also be used as a tool to help neuroscientists constrain models of neural processing. In conclusion, we've developed a sensor that can predict 3D contact point locations at each instant in time instead of relying on temporal information. Our system geometry, specifically the linear taper, is what helps us permit a unique mapping, and our results suggest the potential for high-quality contour extraction without any calibration at all. Thank you for listening, and I hope you come to my poster later.
Baxi Chong will be the next presenter, and he will be talking about back bending and leg motion and how to coordinate that. Please.
Hello, everybody. I'm Baxi Chong, and today I will be here presenting the coordination of back bending and leg movement for quadrupedal locomotion. And it's a collaborative study by Robotics Institute in Carnegie Mellon University, and the School of Physics in Georgia Tech, and the University of Oviedo and Royal Vet College in London. And the framework of this is an overview of our talk today. So there are three subjects: geometry, biology, and robotics. First, we use geometry to study animal locomotion and to understand the principles behind the biological motions. And we use geometry to design gates for robots, and to coordinating the back bending to leg placement. And the biology animal and the robots are counterpart to each other. So on the one hand, we can reproduce the gait used by animals in robots, and second, on the other hand, we can test some gaits less used by animals in robots, which is here of the topic of our studies today. And here's a brief introduction to geometry mechanics. Geometry mechanics is a tool to visualize and design gaits. And we consider the gait as a cyclic motion of internal shape changes. And we can see that the internal shape changes can map to the rotation and translation in the world frame. And this mapping and this design process can be visualized by the height function, which is shown below. And it's very intuitive that the gait, which is the black circle, with the maximum volume enclosed, will produce the largest stride displacement. So we apply this work and extend this work to systems with hybrid contacts, which is the quadrupedal locomotion. So in order to doing so, the very first step is to do the dimension reduction, which is shown on the next slide. I'm sorry. Extending geometry mechanics to the hybrid contact systems. So we use one variable, which is gait phase, to prescribe all the leg motions, all the shoulder angles, all the activation angles, which counters the leg shape, which is the shape variable for leg motions. And there's body shape, which is quite simple, which is how the body is bent. So these two variables will make a shape space, which is the total shape space, how the leg and body coordinate. So we can have the shape space and map this back to the rotation and translation in the world frame. And so in this way, we can extend geometry mechanics to the systems with hybrid contacts. So here's an example of the forward motion. We can have the different gaits with different speeds depending on how we prescribe the leg movement. Just take the trot gait, for example, and we coordinate the back bending to the leg placement by this height function. The proper coordination of leg placement and body bending is the gait with the gait in the blue circle, in the blue curve, which includes the maximum red area underneath. So as you can see from the videos, that the optimum gait outperforms the neutral gait, which does not use the back bending at all, which is also better than the case if we use the back bending to prevent the animals from going forward. So this is the sequence. We can see that the proper coordination is better than no coordination, than the worst coordination. Here's another example in rotations. You can see that and lateral motions, You can see that the gait with optimum back bending coordination will have better in-place turning speed and will have better lateral motion speed. And finally, we link our study to the biology, to the animal studies. And we have some little lizard moving here, and we track the lizard data, and we plotted the lizard motion data together with our optimized design gait in the same plot. As you can see that the green curve, which is the animal tracking data, is matches very well with the blue curve, which is predicted gait in geometry mechanics. So you can see that for both trot, fast walk, and slow walk gait, this back-bending coordination matches very well with the animal tracking data. So at least we can see that it is a way to see the animal locomotion. And here's acknowledgement for Dr. Chawei, Dr. Guillaume, sorry, and all the other collaborators. Thanks.
The third talk of the session is presented by Vincent Groenhuis, and it's about dual-speed, magnetic resonance-safe pneumatic stepper motors.
Thank you. So I'm Vincent. I'm going to talk about pneumatic stepper motors. The challenge is to design a surgical robot inside the MRI scanner for breast biopsy. Such a robot is actuated by pneumatics. Because of the long distance between the robot and the controller, the maximum stepping frequency is limited to about 10 steps per second. So you have the trade-off between accuracy in small steps or speed. State-of-art robots are slow because to have to be precise and they make small steps. You can see that it moves the tip only very slowly. Our solution is to make dual-speed stepper motors. Here you see one example of a pneumatic linear stepper motor with 2 speeds. The small step can move in steps of 0.3 millimeter and the large step in 1.7 millimeter. Together, it allows for a high speed of 20 millimeters per second, but also very small steps. It has a force of 25 Newton. It has no backlash, but it has hysteresis. You can see this at a posterior session. And so the operation of the stepper motor, it uses 2 pistons per side, which move alternately up and down. The small step uses center 2 cylinders, and the large step the outer 2 cylinders. Besides the linear stepper motor, we also made a rotational one. This also has 2 sides with different step distances. We fix one part, and either this part is moving or this one. Together, you can have large speeds when turning in the same direction, or very small steps when going in opposite directions. I have 2 videos to show. First is the linear stepper motor. The second one is of a physical robot to Sunrem 5.
Sunrem 5 is a surgical robot driven by pneumatic stepper motors. The clinical challenge is to target lesions that are only visible on MRI. A manual biopsy may be inaccurate, so several robotic systems have been developed with gradually improved specifications. Sunram 5 is the 5th generation breast biopsy robot. It has a versatile fixation system to immobilize the breast. Dual-speed motors allow both fast and precise movements. The MR conditional biopsy needle is the only metallic component in the entire system. After angulation, the needle is inserted by another dual-speed motor. After confirming the needle position on MRI, the biopsy gun is fired to obtain a tissue sample. The specimen is removed for pathology assessment. In case of emergency, it's possible to eject the needle immediately. Sunram 5 is a major step forward in the field of MR-safe robotics.
Thank you.
And now for the final presentation of the session by Amir Memar about variable stiffness gripper with antagonistic magnetic springs for enhancing manipulation.
Thank you. Hello everyone, my name is Amir Memar from University at Buffalo, and today I'm going to present my work on the design aspects of a variable stiffness gripper and its application to dynamic manipulation. So introducing the concept of variable stiffness actuation in the design of grippers not only can improve the safety aspects of the manipulation, but it can also enhance dynamic tasks like hitting and regrasping. And in fact, some of the key features of a fully VSA-based arm can be achieved at a lower complexity and cost by using variable stiffness grippers along with conventional stiff arms. Here we have our design concept, which is a simple two-finger parallel finger gripper, and the repulsive magnets are used as nonlinear preloaded springs between the actuators and fingers. This results in we can actually control the position and stiffness of the fingers simultaneously by controlling the air gap between the magnets. Using the magnets provided us with different advantages like tolerance to misalignment, compactness, and lightness, which is essential in the design of the grippers. By decoupling the passive deflection of the fingers, we can sense external forces at each finger separately. This is useful when we have uncertainty in the position of the object. Also, the simultaneous passive deflection of the fingers improve the grasp safety if some collision happens. Here we have our mechanical design. Timing belts and pulleys along with two identical servo motors are used to control the position of the actuated magnets, which are mounted on linear sliders. And here you see the prototype of our gripper. So we investigated different approaches to model the magnet repulsion force. It turns out that the theoretical model is not suitable for small air gaps since it considers the magnets as electric dipoles. So we did numerical simulation based on FEM methods and model fitting. So as I mentioned, in addition to the manipulation safety, a class of dynamic manipulation task in which we need a high object velocity at a short period of time, larger than the end effector velocity, can be done with the variable stiffness gripper. Hitting task is a common example of this scenario. So we investigated a hammering task in which we had a small hammer to hit a nail into the foam. So for the sake of simplicity, we use a simple straight back and forth motion of the end effector, which is optimized for a low stiffness setup for comparison purposes. This optimization, this optimal stiffness problem leads to a trajectory optimization problem of the actuated magnets, which the cost function is maximizing the kinetic energy of the hammer at the nail position subjected to the hammer's dynamics and a set of constraints like motion constraints, actuator limits, and of course ensuring an active grasp. To solve this problem, we use a transcription method to convert our TOP problem to a nonlinear programming problem by parameterizing our unknown trajectories with BSP lines and calculating the cost function and reinforcing the constraints at a set of collocation points. Here you see the results. The red shaded area on the left side shows the distance between the actuated magnets, which is related to the level of stiffness during the arm motion. If you're interested in the interpretation of the results, I can explain it on my poster session today afternoon. And we did an experiment with 3 different setups: a high stiff setup, which is the worst case, a lower constant lower stiffness setup, which approximately do a good hitting task. And the last one is the optimal variable stiffness one, which we could significantly improve the hitting task. Thank you for your attention.
So I would like to ask the 4 speakers back onto stage. Hannah, Baxi, Vincent, and Amir. And then I would like to ask you to give us your questions. Actually, don't see too much. There's a question right there.
I'm going to throw this to you.
Okay, for Hannah, so with the whiskers, they're obviously pretty light, but you're moving them to tap and making other movements with them. Maybe I missed this. Are the inertia, do you compensate for the inertia of the whiskers all in your model?
Okay. In the current model, we're not compensating for the inertia because it's all quasi-static, but we're actively looking into the dynamics of the whisker itself. And if we're actually whisking and moving the whiskers as we're doing it, we can account for it by doing like a free air whisk, for example, just to account for any oscillations that are caused just by the motor moving. And then we expect that during contact, all the oscillations will be damped out and everything will be in the quasi-static condition, which is what we're trying to predict.
There's a question back there.
My question's on the quadrupedal work.
To turn it around, the microphone is at the other side. Oh yeah, you're right, okay.
Thank you. Specifically, what ground contact and frictional model did you use to be able to derive a valid local connection?
The ground is sand, so we use resistance force theory to drive all the local connection matrix. It can be seen in the paper and the poster. Thanks.
There's a question right there.
I also have a question for Hannah. In case you have large deflections, how do you measure the radial distance when the object that you're measuring is slipping away along the whisker?
That's an excellent question. And in the work that we're showing here, we're limiting it to deflections below 20 degrees. So we would not expect that the object would slip at all. The model that we are actually using does predict slip and notifies us of slip, and those points were omitted in the actual mapping.
If people up there, is there a microphone upstairs? So you're allowed to ask questions too? experience is if you wait long enough, somebody will do it. Otherwise, I can ask some questions, but your questions are probably more interesting than mine. Tension is rising. Was that a question back there or just waving at somebody? I'm going to take it anyway. Okay, well, I'll ask a question, and I would like to ask you to think about other questions that you might have. Yeah, Baxi, about the backbending, the question is not actually about your paper, but in terms of an evolutionary advantage, why did this evolve this way, right? You could imagine other designs where the legs are closer together, and therefore you can maybe spin faster. Do you have any insight as to why?
I guess it's quite related to something like the snake motion. So it might be something like binary evolutions, like from snake to lizard, lizard to snake, things like that. So
that actually makes a lot of sense. There's a question?
I also have a question for the first paper, the whisker. So have you considered the case where you have multiple contacts or like a line contact for the whisker?
We have not considered that expressly because everything is done at each point in time. So if I'm understanding your question correctly, you'd be able to determine a line just because of, I'm understanding what you're saying, correct, right?
Well, if you have the case where you touch multiple points at the same time on the whisker.
Oh, I see.
Yeah, is it, can they, are the force and torque created by the two-point contacts linear, or I don't know?
I see what you're saying. No, we're just considering one-point contact along the whisker, at one point on the whisker, at the same, yeah.
You see anything? Maybe I'll ask a question to both Vincent and Amir. You both presented ways of actuating robotic, I guess, manipulators, ultimately. Can you speculate on how easy it would be to take those actuation mechanisms and translate them into other robotic, for example, like a hand or other parts of a robot?
Yes, of course, that's one area we're working on that. Here is just a simple two-finger gripper as a proof of concept, but of course the concept of variable stiffness actuation is very important, both for safety, for doing dynamic tasks. Yeah, here using the magnets provide us with the possibility to going smaller scales, probably in the size of the fingers. And that's exactly one approach that we can take in the future.
In our case, we have developed motors in different sites, both very small and large. The pneumatic stepper motors are useful in other applications. For example, when no electricity can be used. The point is that it has no metallic parts, so it can be used in MRI and when you have high voltage or radiation. So there are indeed many other applications.
Thank you. Okay, maybe one last question. You guys can do it. Come on, you had coffee.
So a question on the variable stiffness actuation. You guys have probably thought about using electromagnets to regulate stiffness instead of moving the magnets. So how do those two compare?
So basically, if you want to use electromagnets, probably using coil or voice coils, usually it's going to take much more space, it's heavier. But yes, you can use like voice coil, but for the like gripper or hand approach, it's not a good approach due to the size and energy limitations. Probably, if you want to have like multi-finger hand with variable stiffness actuations. You can use magnets and like cables to actuate them, which can make that compact. But with like voice coils or electromagnet solution, you cannot have that size and the limits which is imposed based on that.
Okay, I would like to thank all of you for your questions, and I would like to ask you to thank all the speakers for the great presentations.